let's start with the last one because that one's fresh in my head after we talked about it. Fibonacci sequence. Never heard of that, right? That's something new. Let's see. Number 4. T1 equals T2 equals T3 equals 1. And then they give you a rule that says Tn is equal to T sub n minus 1 plus T sub n minus 2 plus T sub n minus 3 for all n greater than or equal to 4. And then you're asked to prove that T sub n is less than 2 to the power of n for all those n, right? So that's what you're asked to prove. And let's write it down. Let's start with our real base and then we'll do the 4. We already see that T sub 1 is equal to T sub 2 is equal to T sub 3 is equal to 1, which is less than or equal to, what's the lowest case for all these n? What would show that this is true just in one sentence? What should I put here? Say it again. 4? That'd be 2 to the power of 2. What's the lowest case?
4.
1. All of these are less than 2 to the power of 1, so that means it's certainly less than 2 to the power of 2, which means it's certainly less than 2 to the power of 3. Do you agree?
Isn't it for all n that is greater than 4?
Yeah, but I'm just starting with this is my base before even doing my base case. Just making sure we have somewhere to stand on. All right, and now T4, well, that's equal to the sum of these 3, T sub 3, T sub 2, T sub 1. One plus 1 plus 1 is 3. And we're going to ask, is that less than or equal to 2 to the power of 4? Well, that's 16, so that's true. Again, how these proofs progress with induction is you're trying to say that the sentences follow for all n in between 1 and k. This is the next step, right? Saying that all of these are true. It's like the dominoes. You push one over, you get to the kth one, it falls over, and then you're going to try and prove the one after that will also fall over. So therefore, it works for all. So let's assume that T sub k, which is equal to T sub k minus 1 plus T sub k minus 2 plus T sub k minus 3 is less than 2 to the power of k. And now let's prove the k plus 1 case. And let's ask what we're trying to get to. So this is important. Where are we trying to get to? T sub k plus 1 we want to show is less than 2 to the power of k plus 1. So that's important to know where you're going. Maybe we haven't emphasized that enough. You have to know where you're going. This is what I'm trying to get to. Well, T sub k plus 1 is equal to T sub k plus T sub k minus 1, right? Subtract 1 from this, you get here. Subtract 2 from this, you get here. Plus, subtract 3 from this, T sub k minus 2, which is definitely less than, because we know it's true for this, this, and this. 2 to the power of k, 2 to the power of k minus 1, 2 to the power of k minus 2. So 2 to the power of k plus 2 to the power of k minus 1 plus 2 to the power of k minus 2. So look where you're trying to get to, and then tell me, what do you think I should try and make that right-hand side become? What needs to be there? If you look back at what you're trying to get to. Just look, where are you trying to get to on the right-hand side? So you need something like this, right? And you definitely need the power to be k plus 1. Well, you can factor 2 to the power of k plus 1 out of all these if you know your rules of exponents. So do that. This is equal to, let's see, 2 to the power of k plus 1. If you factor that out, then what's left here? From this guy. 1 over 2. 1 over 2. What's left here? 1/4. And 1/8, right? Okay. Well, what's this equal to? 2 to the power of k plus 1 times, I think we already talked about this. This was how much? 7/8. This is 7/8. How am I going to get to where I want to get to? How am I going to get to here? What's that less than? 2 to the power of k plus 1, right? Right? So it seems so clear after you do it, right? Yeah? No? Well, let's talk about it if it doesn't. It should be clear, right? All of these steps follow logically. This is from the rule. This is just factoring. It's not intuitive, I agree, but if you look back at where you're trying to get to, right, you say, oh, that's probably why I need to pull that out, right? So we did that. Then we just noticed a little algebra in our head. I'm trying to show this is less than that. Well, 7/8 is less than 1, right? So I can make this statement. That's true. And there you go. By induction, you can end your proof because you prove that it's true for all integers, right? Greater than or equal to 4. Yep, Lucy? What determines that we're finished? This, we're trying to prove this is less than this, right? Well, this is less than this, is equal to that, is equal to that, is less than that. So if you just follow through that logic, isn't this less than that? Mm-hmm.
So you're saying that the left side is still is just k plus 1.
Yeah, the left side is still this t sub k plus 1. It's equal to this. It's less than this, which is equal to this, which is equal to this, which is less than this, right? Transitive property. So this is definitely less than this. Yep.
I proved it a different way. Can I
Sure. You want to show it? Yeah. All right. Let's get another way.
Can I write it on the whiteboard?
Sure. You want to go whiteboard? Go for it.
So you assume that it's true for k minus 1 to so that's all under k.
Mhm.
So that's the example showing that you made.
Oh,
That means you have to do minus 1, basically.
Right. So we did 1, 2, 3, and then we proved it with 4, and so that covers all the ones that are inside of the definition.
So the coverage for this one, and then is that all we need?
Well, and then when you cover for 4, it should be
I'm
just like
trying to prove that.
because 4 covers this 3, and then it's good point. But it's like
That was the one thing I remember forgetting. Is it just because like how many on the strong? How many you have to do?
Yeah. That's the one that's always glossed over.
He was like, you do actually
carry
that.
left side down. So like, if t to the k plus 1 is less than 2 to the k plus 1 times 7. This is always
Talk us through it,
smaller
man.
than that.
Okay, so we have
Because it's smaller than that.
we know what t to the k or t sub k equals, and we're trying to, and we assume that t sub k is less than 2 to the kth power, and we want to prove this here that t to the sub k plus 1 is less than 2 to the k plus 1 power. So what I'm going to do here is substitute this into that for tk. And then you'll notice we can combine some like terms here. And so then I looked at this and I'm like, okay, it almost looks like 2 times t to the k, because if we multiply t to the k times 2, we'd have a 2 coefficient on all of these, but we don't have a 2 here. And this is useful because if we are to say like, so because we already assumed that t sub k is less than that, so that must mean 2 to the t sub k is less than 2 to the kth power, right? And so if we want to prove this, we can use our exponent rules. And we know that t to the sub k plus 1 is less than 2 to the t of k. We look and these are equal here. So if this is less than that, and this is less than this, thus this is less than that. Does that make sense?
Yeah, let's see. So substitution.
Here, I'll run through it again.
Yeah, please do.
Okay. So, for this Fibonacci sequence, a term is defined as the last term, 2 terms before that, and 3 terms before that, the sum of that, right? So we have our definitions for t sub k and t sub k plus 1, and we can sub in the definition of t sub k into this, and it is less than 2 of t sub k, and we know that 2 t sub k is less than 2 times 2 to the kth power, and since we're trying to prove that t to the sub k plus 1 is less than 2 times 2 to the kth power, and we know that this is less than that, which is less than that, thus this must be less than this.
I buy it. Does anybody have questions for him? That's a novel way to do it. I like it. Anybody have questions for him? Very good. All right. So always creative way to do these proofs, right? So that's yeah. If you come up with novel ways to do it, I always love hearing them. That's good. Anybody do the 6th one, which was the 3rd one? That was. Let's
Which
do.
one just has the K button?
Say it again.
Which one? I know what
Anybody want to show? I got 2 people who said they did it. Anybody want to show 6? Help each other out? Yeah? Want to come up and do?
the same answer. Let's see if I actually got it.
Yeah, let's do it. Let's see. And that one was there was a typo.
This one, yeah, for Ed.
Mm-hmm.
So just like follow, see if this makes sense to me. Like, I pulled out the 1 plus x over here.
Okay.
And then once you have this one, this right here, you can sub in this
Mm-hmm.
from your base case. If you multiply that out, you get this. Subtract the 1 on the other side. And then it's same thing over here. Subtract them, so then you get kx squared is greater than 0. And the first one that they give you is like 0 or anything greater. Does that work?
Let's see here. So you said you're trying to show that this is true.
Yeah. Mm-hmm.
So then you said this is
Which is just following the formula.
right. So then you're separated.
Mhm.
You said this is greater than or equal to. We're still asking the
Yeah,
question,
yeah.
right?
Mm-hmm.
Then you
Just all the way
said-
down.
Yeah, walk us through it.
Cool.
And then
And
let's
you
see.
subtract this at the end. Just that's the only thing. Right here.
Subtract. Oh yeah, subtraction is
Yep,
fine.
cool.
Yeah. Let's see how this one goes.
Oh,
Do you want to do it on there, up at the
I'd rather do it here.
up here?
Yeah.
Okay. Mm-hmm.
base case is like p to the 1 equals 1 minus x to the 1, because we're just filling in for the n, is greater than or equal to 1 plus x times 1. Then you just get, for this one, this is supposed to be a plus. 1 plus x equals 1. So that checks the base case, works out. We're assuming pk. Which is 1 plus x to the k is greater than or equal to 1 plus kx, which is just coming from our formula that they give us. And so then we have to prove pk plus 1, which is x to the k plus 1 is greater than or equal to 1 plus k plus 1 to the x. And this is where we have to pull apart the 1 plus xk to plus 1 to just be, so this is a question. So 1 plus x times 1 plus x to the k, which just comes from the k plus 1, is greater than or equal to, we're just going to leave the other side the same. 1 plus k plus x. And then we can substitute back in for the 1 plus x to right over there, which is the same thing. 1 plus kx, which is greater than or equal to 1 plus k. And then if you multiply this out, you just get 1 plus x kx plus kx squared is greater than or equal to 1 plus k plus 1 x. If you simplify this, you end up getting the 1's cancel out, so you can just subtract them. And then, so it's x k plus 1 coming from these two terms, plus kx squared is greater than or equal to k plus 1x. You can subtract that off because it's the same. So then you get kx squared is greater than or equal to 0, which if you plug in anything, it's going to get you an answer.
Okay. So this is good. Do you want to ask Natalie a question?
Yeah, Jaden.
So
I don't quite know like how it works, but I'm
where did you show k plus 1? P of k plus 1 to be true.
is what?
Right, so you showed that. Where did you show that p of k plus 1 is true?
This whole
By
process.
assuming a p of k.
Because the k can be, the k just like subs in for the n, so it can be anything. So if you plug in anything to these, they end up working out.
Yeah,
Like,
this does work because, okay, she's trying, this is a question mark. All of this is a question mark, right? She's saying, do I arrive at something that's true, right? Is this true? Well, yeah, x is greater than -1, which means what? It's going to be positive or 0. Lowest it can be is 0, so that's true. If it's negative, well, square it, it's still greater than 0.
I'm not saying that that's not true.
Yeah.
We're meant to show that, what is it? 1 plus x to the k plus 1 is greater than or equal to 1 plus k plus 1x.
Right, and so this is what she's asking, right? This is the k plus 1 case right here.
Yeah.
And she follows it through, like she's still asking the question. She arrives at a statement that's true, so that means going backwards, this must have been true. Or sorry, this must have been true, which was p of k plus 1. So, does that answer it? It's a little bit off way of doing it, but I don't see anything logically wrong with this process. You're asking a question. If you arrive at something that's true, then this statement must be true. So nice job, Nat.
Well, just it's more. It's for you.
Oh.
So we never we don't always have to plug in if we can like a PK, right? If we're able to prove a statement true just by itself, then that's enough for induction to it.
If you're
Because
in,
often for these like problems, like we'll go back when we're proving PK plus 1 is true, we'll use like PK.
yeah.
We don't
And-
necessarily have to. We don't have to. It just helps a lot.
Well, Natalie did that. She wouldn't have been able to prove that statement true if she hadn't used the Kth case. So she did use P of K.
Just in general, do we have to?
The point of an induction proof, why it's helpful, is because you need the Kth case to
To be
prove.
able to plug in.
Yes, to be able to.
So we will always have to.
Yes. And let me show you another way. So this is actually, it goes back to what you just proved at the end there, that true statement. So this is another way of doing it. Let x be a real number greater than -1, right? And we're going to write a paragraph. Then, let's see. 1 plus x is always greater than 0. So we agree with that. For the base case, n equals 1, what do we have? We have 1 plus x to the 1, and is that greater than or equal to 1 plus x? Well, it's clear that that's true. So for your next sentence, assume the Kth case is true. That is 1 plus x to the power of k greater than or equal to 1 plus, what is it, kx? Is that right? Okay, so we assume that, and assume that for all n in between 1 and k. So assume that for all n in between 1 and k. So that's the Kth case. Next sentence, show P of k plus 1 is true. Well, so let's just do that by going through and showing that that's true. Algebraically. P of k plus 1, so that'd be 1 plus x to the power of k plus 1. Well, that's equal to 1 plus x times 1 plus x to the kth power, which is greater than or equal to, from the inductive hypothesis right here, 1 plus x times 1 plus kx. Well, like Natalie did, and you saw this in her proof, you expand that out, which is equal to 1 plus, let's see, we get kx and 1x, so we get k plus 1x plus kx squared. All right. X squared is bigger than what? X squared is bigger than 0. X squared is bigger than x. You're right, but it's the important thing is that it's bigger than 0. So, isn't this bigger than, actually strictly bigger than, 1 plus k plus 1x? Isn't that true? Yeah, because kx squared, k is greater than or equal to 1, right? X squared greater than 0. So we can eliminate it. We've shown that this is equal to that, is greater than or equal to that, which is greater than that. So this definitely must be greater than or equal to that, which is what Natalie proved too, but in a different way.
Just a step where you say 1 times x times 1 times x to the k is greater than or equal to, yeah, where do you get that statement?
I get this statement from, right here is my inductive hypothesis. If I times both sides by 1 plus x, which is fine because 1 plus x is greater than 0. And that's why I made this statement up here. Greater than 0. I know this sign will not switch. So this times 1 plus x to the k, right? If I just do that to both sides, right? Do you see that?
Yeah,
Yeah.
I know.
Yeah, so.
Thank you.
Yeah, it's Good question. Yeah, because a lot of the time some of these things are hiding from you. You have to search for it. All right, so yeah, good presentations today. That was good. Do you feel comfortable with induction proofs? Some no, some yes. Contradictions? Yeah. Sometimes direct proofs. We've done a couple of those. Yeah. You want to do an epsilon delta proof? Yeah.
What is that?
We did one of those on the class. We did one the first day we started proofs. Let's see. Let's do one more and then I'll give